Students, in previous lessons, you learned that all elements are composed of tiny, fast-moving particles called atoms. Atoms compose all ordinary matter. If you want to understand matter, you must begin by understanding atoms. During this lesson, we will consider some fundamental ideas about atoms. Collect definitions for these keywords when listening to this lecture. It's important to understand these words. Make sure you will understand the concepts behind these terms. If you cut a piece of graphite from the tip of a pencil into smaller and smaller pieces, how far could you go? Could you divide it forever? Until about 200 years ago, even a scientist thought that matter was indeed continuous, but they were wrong. The first people to propose that matter was composed of small, indestructible particles were Greek philosophers Leucippus and Democritus in the 5th century BC. However, at the time, the atomic idea was rejected by most Greek thinkers. In the beginning of 19th century, certain observations led the English chemist John Dalton to reformulate the atomic theory. By the end of the 19th century, scientists were convinced that matter was composed of atoms, supposedly indestructible building blocks that composed everything. However, further experiments revealed that the atom itself was composed of even smaller, more fundamental particles. An English physicist named J.J. Thomson discovered the electron. Through experiments examining the properties of cathode rays, he deduced that electrons were negatively charged. The nucleus was discovered in 1911 by Ernest Rutherford, a physicist from New Zealand. In 1920, Rutherford proposed the name proton for the positively charged particles of the atom. He also theorized that there was a neutral particle within the nucleus, which James Chadwick, a British physicist and student of Rutherford's, was able to confirm in 1932. Niels Bohr was a Danish physicist who developed the Bohr model of the atom, in which he proposed that energy levels of electrons are discrete and that the electrons revolve in stable orbits around the nucleus, but can jump from one orbit to another. Because of its simplicity, the Bohr model is still commonly taught before moving on to the more accurate but more complex Schrödinger model. The Schrödinger model assumes that the electron is a wave and tries to describe the regions in space where electrons are most likely to be found. The Bohr model is a one-dimensional model. Schrödinger's model allows the electron to occupy three-dimensional space. Eventually, as you divide the graphite, you end up with carbon atoms. These are no longer divisible, not just because of their sheer smallness, but because of the nature of matter. You remember from our previous lesson that pure chemical substances that can be decomposed on other substances are called compounds, yhdisteet. When you place a piece of sugar, sokeri, into a test tube and heat it, sugar melts, then its color changes to brown. If heating continues, the liquid becomes more and more dark and viscous, and finally it becomes a black solid. Further analysis shows that the solid formed is carbon, hiili. Numerous attempts made by early chemists to decompose carbon failed, so it is an element, alkali. An atom is the smallest unit of matter that retains all of the chemical properties of an element. You can not divide a carbon atom into smaller pieces and still have carbon. The word atom comes from the Greek atomos, meaning indivisible, as it was once thought that atoms were the smallest things in the universe and could not be divided. We now know that each individual atom consists of smaller particles. Separating these smaller constituent particles requires ever-increasing amounts of energy. Even though atoms are not really indivisible, they are chemically indivisible. The atoms are the units of chemical changes. Chemical reactions involve the combination, separation, or rearrangement of atoms, but in a chemical reaction, atoms are neither created nor destroyed, and atoms cannot change their identity, and they are not divided into parts. The atom consists of a tiny nucleus surrounded by a cloud of electrons that move about the nucleus. As we will see later, the chemistry of an atom mainly results from its electrons. For this reason, chemists can be satisfied with the crude nuclear model. The nucleus contains protons and neutrons. This time it is very easy to learn the Finnish terms as they sound like their English equivalents. Atom, atomi. Electron, elektroni. Neutron, neutroni. Proton, protoni. The only difficult one is nucleus, ydin. Protonit ja neutronit ovat ytimessä. Elektronit kiertävät ydintä. Protons and neutrons have approximately the same mass. However, one proton is about 1,800 times more massive than an electron. A common unit to express these masses is the atomic mass unit. Expressed in this unit, the mass of a proton or neutron is approximately 1. The charge of the proton and electron are equal in magnitude, but opposite in sign. So, when the two particles are paired, the charges sum to 0. The neutron has no charge. The electrons of an atom are attracted to the protons in an atomic nucleus by the electromagnetic force, sähkömagneettinen vuorovaikutus. The electromagnetic force is one of the 4 fundamental forces in nature. Electric charges attract or repel one another. Unlike charges attract, like ones repel. As oppositely charged particles attract each other, vastakkaismerkkiset voimat vetävät toisiaan puoleensa, electrons are kept in the orbit around the nucleus. The protons and neutrons in the nucleus are attracted to each other by the nuclear force, the strong force, vahva vuorovaikutus, which is also one of the four basic forces in nature. This force between the protons and neutrons overcomes the repulsive electrical force that would otherwise push the protons apart according to the rules of electricity. Viewed simply, electrons are arranged in shells around an atom's nucleus. Each shell can only carry a set number of electrons. Electrons closest to the nucleus will have the lowest energy. Electrons further away from the nucleus will have higher energy. The main rule is that the filling of the shells with electrons proceeds from the shells of lower energy to shells of higher energy. Thus, the electron shells of an atom are populated from the inside out. The valence shell is the outermost shell of an atom in its neutral state. Electrons in the outermost shell of an atom are relatively loosely bound to the atom. That is why the valence electrons, valence electrons, are most likely to be used in reactions. All atoms are roughly the same size. A convenient unit of length for measuring atomic sizes is the ångström, 1/10 billionth of a meter. The radius of an atom measures 1 or 2 ångströms. So, approximately 100 million or 50 million atoms of a solid matter lined up in a row would measure 1 centimeter. Compared with the overall size of the atom, the nucleus is even more minute. It is in the same proportion to the atom as a marble is to a football field. Electrons are also very small compared to protons and neutrons. So, with all this empty space, why don't solid objects just pass through one another? The answer is that the negatively charged electron clouds of the atoms will repel each other if they get too close together. If all atoms are composed of the same subatomic particles, then what makes the atoms of one element different from those on another? The answer is the number of these particles. The numbers of particles in an atom can be calculated from its atomic number, järjestysluku, and mass number, massaluku. The number that is most important for the identity of an atom is the number of protons in its nucleus. The number of protons in an atomic nucleus is called the atomic number, järjestysluku, and given the symbol Z. Since atoms have no net charge, the number of electrons must equal the number of protons. The sum of the number of neutrons and protons is called the mass number, massaluku, and given the symbol A. The number of neutrons is the difference between the mass number and the atomic number. You have learned from previous lessons that elements are substances that cannot be decomposed into simpler substances by chemical or physical means. Gold atoms cannot be broken down into anything smaller while still retaining the properties of gold. Now you will learn a new definition of an element, alkali. An element is a substance whose atoms all have the same number of protons. Another way of saying this is that all of a particular element's atoms have the same atomic number, järjestysluku. Each element is distinguished by its atomic number. The number of protons defines the element. An atom with 2 protons in its nucleus is a helium atom. An atom with 6 protons in its nucleus is a carbon atom, heliatomi, and so on. The number of protons in the nucleus determines which element an atom is, while the number of electrons surrounding the nucleus determines which kind of reactions the atom will undergo. Although each element has a defined number of protons, the number of neutrons is not fixed. Atoms with the same atomic number but variable mass numbers, that means variable number of neutrons, are called isotopes, isotopit. In a room where chemistry is taught, a chart called the periodic table, jaksollinen järjestelmä, is almost certain to be found hanging on the wall. This chart shows all the known elements and gives a good deal of information about each. The letters in the boxes are the symbols for the elements. The number shown above each symbol is the atomic number, järjestysluku, number of protons for that element. Elements are placed in order based on the atomic number, how many protons they have. In a neutral atom, the number of electrons will equal the number of protons, so we can determine number of electrons from atomic number. The position of an element in the periodic table provides useful information about how those electrons are arranged. A period in the periodic table is a horizontal row of chemical elements. All elements in a row have the same number of electron shells. For example, the fourth period contains 18 elements, beginning with potassium and ending with krypton. And all these elements have 4 electron shells. As atomic number increases, protons are added one by one to the nucleus to build up the elements. Electrons are similarly added to shells. Each next element in a period has one more proton and so also one more electron than its predecessor. As atomic number increases, shells fill with electrons. The filling of each shell corresponds to a row in the table. As I told you, each shell, kuori, can only carry a set number of electrons. A new period begins when a new energy level begins filling with electrons. The first shell can hold up to 2 electrons, That's why period 1 has only 2 elements, hydrogen, vety, and helium. The second shell can hold up to 8 electrons, and that's why second period has 8 elements. The outermost shell, the valence shell, can accommodate only 8 electrons. Having a maximum of 8 valence electrons explains why, from the third shell onwards, the next shell begins to fill before the current shell is full. That is why there is only 8 elements in third period. The third shell could hold up 18 electrons, but when the third shell contains 8 electrons, the fourth shell begins to fill. That is, the fourth shell begins to fill before the third shell is full. Similarly, when the fourth shell contains 8 electrons, the fifth shell begins to fill. A vertical column of elements in the periodic table is called a group, ryhmä. The periodic table can be broadly divided into main group elements, whose properties tend to be largely predictable based on their position in the periodic table, and transition elements or transition metals, whose properties tend to be less predictable based simply on their position in the periodic table. The elements in the same main group of the periodic table tend to have similar chemical properties. Nowadays, periodic tables list the group numbers in Arabic numbers instead of Roman numerals, and the transition metal groups are included in the counting, so there are 18 groups. Anyway, old-fashioned main group numbers shown by Roman numerals above this table tell us how many valence electrons in the outermost shell there are for each element. In this numbering system, group 13 is main group 3 and group 18 is main group 8. If we use these traditional designations, the group number indicates the total number of valence electrons for the atoms in these groups. For example, all the elements in main group 3 in the boron group have 3 valence electrons. The elements with similar properties align in the same vertical columns because they have the same valence electron configuration, and elements with the same valence electron configuration show similar chemical behavior. All the elements in group 1 have just one valence electron. This makes them very reactive. The group includes the nonmetal hydrogen and 6 metals that are called alkali metals. Hydrogen is a very reactive gas, and the alkali metals are even more reactive as they are eager to lose that one valence electron. A piece of sodium explodes violently when dropped into water. 6 non-metallic elements constitute group 17, main group 7 of the periodic table. They are called halogens. They have 7 electrons in their outer shell. That means they are all just 1 electron shy of having full shells. That's why halogens are highly reactive. Fluorine is the most reactive of the halogens and, in fact, of all elements. When halogens react with metals, they produce a wide range of salts, ionic compounds. The name halogen means salt-producing in Greek. The most stable, mostly unreactive elements are listed in the final column, 18th group and 8th main group. These are all gaseous under normal conditions of temperature and pressure and are called noble gases, jalokaasut. Neon, argon, etc. each contain 8 electrons in their valence shell. Therefore, these elements have a full valence shell that has the maximum number of electrons possible. Helium at the top of this column is an exception because it has 2 valence electrons. Anyway, it has only 1 shell which can only have 2 electrons, so it has the maximum number of electrons in its valence level as well. That's why it is in main group 8, not in the main group 2. Helium, like other noble gases, is chemically stable. It does not combine with other elements to form compounds and is therefore safe to put into balloons.